And let me begin. So today we're going to talk about multi-plane page allocation and about elements from visual entry constructor, pair and unite. Until now, we did discuss with you steps such as how to get physical image, how to do page layout, how to apply ECC correction, inversion, XOR transformation, and also how to perform block management step. If somebody skipped those webinars, they all are available on our YouTube channel. So please go there and you can see all the things, all information there. There are timestamps on almost all videos, and it's quite convenient. You can just select the topic you like to hear, and you can listen it. You can learn some information from there. And today we will talk about page allocation analysis. The last step in like a regular case. First of all, until we begin to talk about the page allocation thing, we need to remember we need to learn internal NAND memory structure. So on this slide, you can see one memory crystal or one memory chip. And normally it consists of next things. It could be page buffers, some peripheral devices which are used to provide interface, like communication of memory chip with the controller. And there are two big things here. It's two planes, 2 or 4 planes usually. One plane, it's an array of memory cells. So the plane is the thing where all information is located, where all the data is stored. And usually NAND memory crystal consists of 2 planes, 2 or 4 planes. So that one plane consists of blocks. I hope that you are familiar with this thing already. Block consists of pages, and pages consist of memory cells. One memory cell is one transistor. So that's the structure of NAND memory crystal. And the thing is that the controller can write pages in 2 ways. But first of all, let's remember what is block and what is page. Page, it's one line of transistors here, and the controller writes data by pages. So page is a minimal amount of data for writing for controller. And block, it's a minimal amount of data for erasing. If it's necessary to erase just one page or one bit in somewhere on some page, controller will erase whole block. So block, and usually it's reads data. Well, about this thing we'll talk later. So block, it's minimal amount of data for erasing, page is minimal amount of data for writing and reading. And the main thing here that you should remember that there are usually 2 planes, and controller can write data by pages in 2 ways into these planes. The first way of writing data would be like this. Controller creates one page of information and writes only one page to one plane only. So for example, to this plane. So it fills this plane with data, and when this plane will be full, then it switches to another plane. So only one page goes at a time here to one plane only. And you can see this scheme here. So page 0 went to plane 0, then next page went to the same plane, next page to the same plane, and so on, until this plane is full. then it will switch to plane number 1 or to next plane. And in this case, one logical block will be equal to one physical block. What is logical block? You will see this better on the example of multiplane page allocation. So one physical block, it's this amount of data. And yeah, now just trust me that one logical block is equal to one physical block in case of single plane page allocation. Now let's see what happens when we have multiplane page allocation. Controller creates like two pages at once if one period. And one page, like for example, let's say that one page has size 4 kilobytes in one plane. Here we have 4 kilobytes and here we have 4 kilobytes. So controller creates one virtual page with a size 8 kilobytes and writes this data simultaneously into both planes, here and here. And of course, all these pages will have the same LBN, same logical block number. So that means that this physical block and this physical block will have same LBN. So that's why we understand that one logical block will have size of two physical blocks here, because data was written simultaneously into two planes. In case if we have 4 planes, then one logical block would have size of 4 physical blocks. And that's why in case of single plane page allocation, one logical block has size of one physical block, because data was written to one plane only, without any paralleling. So in other words, we can say that single plane page allocation works like a JBOD, and just bunch of drives, when two drives are connected sequentially to one to another one. Multiplane page allocation works like a RAID 0, when data is written simultaneously into two planes. This way of data writing, multiplane page allocation, of course, is better because speed will be higher. It's like just 2 times higher speed comparing to this one. So normally all devices, all chips use this way of page allocation. We can say that this way is kind of like a default way of page allocations. Let's see what we have, what we'll get if we have 2 memory chips. Yeah, 4 planes will be faster than 2 planes. And if we have 2 memory chips with 2 planes, then we will get 4 planes in total, and controller can write data simultaneously into all planes here, 1, 2, 3, 4. And one logical block will have size of 4 physical blocks. And that's why, by the way, SSD drives are that fast, because controller can write data simultaneously into all chips, and it provides great speed and big problems when you do chip-off recovery of SSD drive, because you have to assemble many chips together and you have to find order. It's like quite complicated RAID assembly. So that's multiplane page allocation on the chip level. Sometimes on this screen you can see that it's 2 memory chips. It also can be 1 memory chip with 2 crystals. So 1 memory chip, 2 crystals. Each crystal has 2 planes. So in total we have 4 planes for writing, and 1 logical block has 4 physical blocks. This thing you may not remember that good for now, but it's better if you will understand why physical block may be equal to a logical block, or maybe 2 times smaller or 4 times smaller. It's just because of this, because of multiplane page allocation. If multiplane page allocation wasn't used, so physical block will be equal to logical block. If multiplane page allocation was used, then logical block might have different sizes. It will depend on the amount of planes which data were written to. So that's the thing about multiplane page allocation. Until now, is everything clear? Okay, I guess so. And it's all good, it's all clear and understandable for now. And it all works without any problems. But the problem comes when we start to do chip-off data recovery, because there is one peculiarity, there is one thing, that when we insert memory chip into the reader, into the VNR reader, it reads memory chip by whole blocks. So it doesn't read data by pages, like data were written, but it reads data by whole blocks. So it reads this whole block and places this into the dump. Then this one, and we have it here, this one, number 2, this one, number 3. So VNR reads reads data by whole blocks. And let's see what will happen if we have single plane page allocation and multi-plane page allocation. So in case of single plane page allocation, when we get data out of the memory chip to the dump, we don't have any problems because pages were written sequentially into one block. So we get all pages from this block here go sequentially, then this block, all pages go sequentially, and basically everything is good. We don't have any mix here, don't have any additional problems. One logical block equal to one physical block, pages are not mixed within one logical block. No transformation is required in this case. So everything is good. Now let's see what happens if we have multi-plane page allocation. And as I said, this way of data writing, of data allocating, is pretty common, and it's a default, more or less, it's default way of data allocation for majority of memory chips of NAND devices. Okay, so let's see. This is memory chip, right? Data pages were written simultaneously into both planes. So one page went here, next portion of data went here. So we can say that page 0 is here, page 1 is here, and then 2, 3, 4, 5, and so on, right? So now let's see what we get in the dump. First, hold this block was read, and we have it here. Then this next block. Both these blocks have the same LBN, so they both belong to one logical block. It's one logical block here. And we can see that within one logical block, pages will be mixed. Page 0 will be in the first half of the block. Page 1 will be in the second half of the block. And so on. 2, 3, 4, 5, and so on. So pages are mixed within one block. And of course, if you have some picture and block size is, let's say, 4 megabytes, you won't be able to see this picture because, let's say, 8 kilobytes of picture will be here, and then next 8 kilobytes will be here. Everything will be corrupted, and you won't be able to recover any files greater than 1 page size. Data integrity on this step, no more than 1 page. No bigger, no greater than 1 page size. And in this moment, pair element comes to play, comes in game. Pair element can rearrange pages in normal logical sequence within one block. So we need to bring pair element to the workspace connected to the previous element, and it will do all the things automatically. You just need to set page size, this page size, and on this step you definitely know the page size. And then you need to set logical block size, this size, and also on this step you should know the logical block size. And normally you don't need to set all these values at all, because as I said, you know already these values, software knows already these values, and the software will just take it from previous elements. You don't need to adjust it normally in regular case. And the pair element will rearrange pages in logical sequence. So it will take page 0 from the first half of the block, the next page will be taken from here, so page 0, 1, 2, 3, and so on, like this. And after the pair element, pages will be arranged in normal logical sequence, in growing sequence within one block. And data integrity after the pair element will be equal to one block size. If one block size is 4 megabytes, so you will be able to recover data no bigger than 4 megabytes. Basically, many pictures could be recovered after the pair element if there is no any other transformation after the pair. Okay, so this is what happens when we have one memory chip, 2 planes, and multi-plane page allocation. Now let's see. Okay, now let's see how do we detect if multi-plane page allocation was used or if multi-plane page allocation wasn't used. Just let me ask you if everything is clear until now. Okay, great. Now let's see, how can we understand, should we use pair or shouldn't we use? Of course, we know that we should use pair if multi-plane page allocation was used. But how to see this multi-plane page allocation? How can we understand that? It's quite easy, actually. Let's have a look on this slide, and let's imagine that there is some data, such portion of data, and let's say that we can see here portion of data which has size of one logical block. It can be any size, but for better understanding, let's say that this is one logical block. This is one physical block. Second physical block, let's say that if we have here 4 megabytes, so this is 8 megabytes. And let's say that this is a bitmap of the data which we want to write to these blocks. And if we have a look on this bitmap, we will see in the beginning this type of pattern, then some line, then again this type of pattern, and then some diagonal lines. It's the thing is that data looks like a patterns, right? If you will scroll bitmap, you will find different patterns. So user data looks like a patterns. If this is not some archives, some zip files or some video files, pictures, even pictures may have some patterns. I mean, you can see some lines between pictures. But anyway, almost basically all flash devices will have some patterns of data, user data, some recognizable patterns. And let's say that this recognizable pattern is going to be written into the memory chip. And we know that this part of this pattern will be placed into this block, and this part of the pattern will be placed in this block, because data will be written simultaneously, like this, right? And both these blocks belong to one logical block. Then, when we unsoldered the memory chip and read it to the dump, what we will see? First, we'll see this data, this part of data, it's in here, and then this part of data, it's in here. I'd like to remind that it's one virtual block. One virtual block. We can see this by LBN. If we will scroll it to the service area, we'll see that all this data, all these patterns have the same LBN. So we clearly see borders of this virtual block. And then if we will divide this, just like mentally, visually divide this block by 2, we will see repeatable pattern in first half of the block and in second half of the block. We will have repeatable patterns if multi-plane page allocation was used. So once we can find some block where we can clearly see repeatable patterns in first half of the block and in second half of the block, we say that multi-plane page allocation was used. Because in case if single page allocation was used, we will, well, by some coincidence, we can see repeatable pattern, but in most of cases, like 99% of cases, we won't be able to find repeatable patterns within one virtual block. So that's the way how can we understand, how can we see the sign of multi-plane page allocation usage. Now let's see how does it look like on real dumps, on real examples. So that's the single plane page allocation. And let's say that this is one block. This is one block, next block. And we can see that first half of the block is not the same, doesn't look equal to second part of the block. And the same as here, it looks different. So once we found that we have different, very different parts within one block, we understand that single plane page allocation was used. If we can see something like this, so one block divided by 2, just in our head, I mean, we don't use any tools in the software, we just compare visually this part to this part. And if they look similar, we say that multi-plane page allocation was used. Sometimes it could be just like this. You can see it's a noisy looking pattern, but if you have a look more precisely, you will see one line, next line, next line. So 3 lines here, 1, 2, 3, and the same as here, 1, 2, 3. That's all because data was written like this, simultaneously into 2 planes. And like this line here, I mean, this line here, it just proceeding of or continue of this line. That's why we have that repeatable patterns. And that's the way how we detect it. Another thing that, as I said, multi-plane page allocation is very typical, very common for NAND devices. And in most of cases, we have to use it. We may use it like by default, like always. And I mean, the thing is that from the beginning, we always want to use it. We always are going to use it. And we will not use it in case only if we can find something like this. So if you found that first half of the block is nothing compared, is not the same like the second part of the block, you don't use the pair element. If you can't find such block, you will use it, even if you can't find repeatable patterns. It's like in case of ambiguity, you better try to use pair than to not use it. And you can be sure about not using the pair element only if you have something like this. Is it clear? All right. Sure, we're gonna have 4 or 5 cases today, so you'll see how it works. All right. Let's see how we treat the case where we have 2 memory chips or 2 crystals and multi-plane page allocation was used. So 2 memory chips, 4 planes, data was written simultaneously into all planes. After we got these memory chips to dumps, we have 2 dumps and 1 dump has page allocation like this one, next dump has page allocation like this one. So you can see that page 0 is here, then page 1 is here, 2, 3, because this block belongs to this block. I mean, this block is this block actually, this one is this one, this one is this one, and so on. So pages in this case are really mixed. And we need to assemble all of them in a good growing sequence. How are we gonna do this? Well, first of all, since we have 2 dumps, we apply pair element to both dumps, to this one and to this one. In case of 2 dumps, if you remember, we have something like this. So this is 1 dump, this is 2nd dump, and we have 1 chain for each dump, right? So we apply pair element to each dump, to each chain, and after the pair element, we'll have 2 dumps with pages go like this: 0, 1, 0, 1, then 4, 5, 4, 5, 8, 9, 8, 9, and so on. So pages are still mixed in this dump, in this dump. It's but they go in sequence by pairs. Like we have 1 pair of pages here, then 1 pair of pages here, and so on. 0, 1, 2, 3, and so on. After this step, we need to join these 2 dumps, to unite these 2 dumps. And how are we gonna do this? Since pages go in sequence by pairs, by two pages. So we're gonna unite them by 2 pages, right? We will take 2 pages from here and place it into the result dump, then 2 pages from here and place it here, and so on. And after this, you can see that all pages will go sequentially within 1 dump, within 1 block, and you're good to go further. In this situation, 1 logical block has size of 4 physical blocks. Pages, of course, mixed within 1 logical block. And to remove this mix, you have to use pair first and then unite. Element should be used. And you unite these 2 dumps by 2 pages. That's what you're gonna do in case if you have 2 dumps or 4 dumps or even more dumps and multi-plane page allocation. And you should be quite careful with this unite element, because when you use unite element, you need to set amount of data which you want to unite it by. And by default, software automatically set size of 2 pages. Once you connect unite element to these 2 dumps, it will set size of 2 pages. But sometimes you by some reason, you can change it, and then you need to adjust it manually. Somehow you did mistake, and then you need to fix this mistake. So when you will do that fix, you should understand that if here you have, like in the beginning, you have size of page 8 kilobytes. After the pair element, you should use size for uniting, I said 8 kilobytes, yeah, then 16 kilobytes. So double page size should be used in here if you had pair element before. And then you'll get this beautiful sequence of pages. Data will be good within one block, and all you need to do after this is to assemble blocks in growing sequence. Now, let's see how to detect if multiplane page allocation was used actually on chip level. Because there could be situation when we have two chips, each one has two planes, and data was written simultaneously into this chip, into these planes, and then when this chip was full, then data was written into next chip. So we have a multiplane page allocation on inside one chip, but we don't have multiplane page allocation on the chip level. Data was not written simultaneously into both chips. In that case, you will have to use pair element for dumps, and then when it comes to uniting these dumps, you will have to unite them by dumps actually. In this case, you unite it by pages. In case if data was written sequentially to these memory chips, you will have to unite it by dumps. First, you take this dump full, and then this dump full, whole dump. And let's see how you can see if multiplane page allocation was used on chip level. The same approach, you need to, for example, you made ECC correction, XOR transformation pair for one physical image. For this physical image, you just repeat all steps because it must be the same, it will be the same. So you may not even analyze, you may not even open this chip, you just repeat all these transformations, all these preparations for this physical image. Now, after the pair, you understand that you need somehow to unite these two chains. And there are two variants, two ways how to unite them. First variant, you need to unite it by pages in case if multiplane page allocation was used and data was written simultaneously into both chips. Or you can unite it by dumps if data was written first in this chip and then after some time in this chip. And how to see this? You just open both these both these elements together and scroll it together and just compare patterns that you see in one element and in another element. And if you will see same patterns, like on their picture, you see this line here and here, then this like a checkmate pattern here and here, and so on. So you understand that data, it's the same kind of data here and here. Data was written simultaneously. And it just means that you need to unite these two physical images by pages. Another thing that you can check, it's LBN. If you know, if you have LBN on this stage already, you can just compare it in the service area. It's here, F8, F4, and the same is here, F8, F4. Same LBN means that it's one logical block was written into both chips, and it just proves that It's a multi-plane page allocation on the chip level, and you need to unite these two dumps by 2 pages. And that's another case. The same situation, right? You have 2 physical images and all transformations are the same. You open this pair elements and you check these patterns. Here you see more noisy patterns, and here you see more ones, more whitish patterns. And you see LBNs are different. So that means the data first was written here and then in here. And in that case, you unite this and that element by dumps. That means that it will just connect it like a JBOD. Firstly, this data will go to the markers table, and then this one. So this is how you unite 2 dumps, how you treat cases when you have more than 1 physical dump, how you connect it. Here, and on this screen, it's even more interesting. You have 4 dumps, right? 0, 1, 2, 3. And how would you unite them? What we can see here, we see that first pair of dumps has more or less a similar pattern, right? We can see these lines here and there. And this pair also has similar pattern. Patterns are different between pairs, but within pairs they are the same. They're similar, right? So how are we going to unite this? We will unite these two pairs by pages, and these 2 pairs by pages. And then 2 result elements we will unite by dumps. So it's gonna look like this. This one and this one we unite by pages. The same here. As a result, we get 2 unite elements. And then we need to unite this one and this one. And in here, we already united by dumps. And that's it. Then you proceed with markers table and so on. So as you can see, it's quite clear and quite easy once you understand why it happens, the reason of this mix. Once you understand that there are 2 planes, a data could be written simultaneously into these planes. And if you will remember the reason, then you will clearly understand why sometimes logical block equal to physical block, why sometimes it's bigger, why it can be 2 times bigger or 4 times bigger. It's all will be very clear to understand, to figure out, if you will remember this thing about planes. Let me do the sharing of visual NAND reconstructor. And here we have the first case. It's already opened, and the same thing like before. We have everything prepared, but 1 element. And in this webinar, it's going to be about multi-plane page allocation. So let's do the analysis. After the XOR, we remember, based on this scheme, that after the XOR we have that multi-plane page allocation thing. And now let's do the analysis, which I hope you understand now how to do. So I will open the dump and scroll it to some patterns, minimize it, and then I need to detect borders of virtual blocks, of logical blocks. This is a SAM controller, so service area is located in the end. So I scroll it to the end, and in here I can clearly see borders of logical blocks, right? Also, I can use here option to highlight blocks. If I click on this, one block will be highlighted, right? And now I would like to pay your attention that about physical and logical block size in the software, because sometimes it may confuse you. So when you put the memory chip into the reader and you read configuration, you get block size, right, in configuration. And this block size will be used in here, in ECC, in XOR, and so on. And in most of cases, that block size is correct. But sometimes you need to adjust it. And when you may need to adjust it, because sometimes configuration may have physical block size, but since and in the software logical block size matters, because here we use not here maybe, but here we use logical block size. In markers table we use logical block size. With the pair element we use logical block size. So physical block size we almost never use. We use it just in case of a bad column removal procedure. So in the bad column remover here, we need to set physical block size. You can see it here, right? But for all another elements, logical block size is important. And configuration may have physical block size, but sometimes it could be logical block size. So sometimes it could be fully correct. For example, for TLC chips, we usually have physical block size in configuration. And then if you deal with physical block with the TLC chip, so configuration has physical block size, software takes that size for the XOR element, for markers table, and it will be wrong. It will be not correct. And you need to adjust it, because in case if multiplane page allocation was used, because we can't know if multiplane page allocation was used, if it wasn't used. And so we place in the configuration physical block size, and you may have to change it. And you need to change it. How? You can detect it how? Very easy. You just open the bitmap and look for these borders. And if you see, and by the way, highlight blocks option will take block size from the will take the block size which is used for now which is actual for now in this moment, and you can just check if it's correct or not. If you see that these borders, highlighted borders, equal to real borders of LBN, so that means that size, logical block size is correct. But if you have some TLC chip and configuration has physical block size, so here in configuration you have physical block size, for example here, then this physical block size will be used on this stage, on this stage, and this stage. And then when you open XOR element, you may see that this highlighted area is 2 times smaller than these borders. Let me just show you this example. For example, structure view and block size. Now has this size. I will divide it by 2. So this is now logical block size. Physical block size will be this one. Now I insert it, and now I'm simulating a situation when you had in configuration physical block size and you just started to work with this. So let's say that you came until here, and now if you go to the dump, to the area, to the service area, and now you use this highlight option. So you can see that this part of block is highlighted. So you can see what software thinks where logical block is, size of logical block. So this is one, this is next, and so on. But in fact, if you will pay attention, if you will have a look on this service area, you'll see that block starts here, it doesn't stop here, and proceeds until this point. So this is one block. So in this moment, you can understand that software is wrong about logical block size, and you need to adjust it. How you can adjust it? If you see that it's 2 times bigger, then you just go to structure view and change block size here. You set it 2 times bigger. Okay. Now, if you open this, and scroll it to the service area where you can see real borders of blocks, you can see that now it fits. Now it's correct. And that's now I described the situation when block size was not correct. For another chip's configuration may have not physical block size, but already logical block size. So you will not have to change anything. Your block size will be correct from the beginning. So that means that you should just take into account that the block size may be necessary to adjust. All right, so in this case, and by the way, about block size changing and checking and adjustment, you can read on in our knowledge base in the article about Phison dynamic XOR. Yeah, in the article about Phison dynamic XOR, we explain there this situation when from the beginning block size was smaller. So we have in configuration physical block size, but because of multiplane page allocation, logical block size is bigger, so we need to change it in the utility. So you can also check that article for better understanding. So what do we see now here? This is one block, and do you see repeatable patterns in this block? I would say that yes, there is repeatable pattern. In this block, it may not be that much clear, but still, we have one line in here, one line in here. So we say that there is a repeatable pattern. And then here, the same in this case. we also have this repeatable pattern. So basically all blocks, more or less all blocks, have that repeatable patterns, the same as here. So once we can see this picture, we understand that multiplane page allocation was used, and we need to apply pair. We need to use pair element. So we just bring it here, connect it like this, and in here we can set parameters of the pair element. Number of planes, it's 2 in most of cases. And when we may set 4, we will set 4 planes if we, let's say, if we highlight blocks, and in this, within one block, we'll see 4 repeatable patterns. In case if we have 4 repeatable patterns, we understand that there are 4 planes in this case, and in here we should set 4. But in majority of devices, majority of cases, we still use 2 planes, because majority of memory chips have just 2 planes. Movable block size, it's the name for the page. So we have here page size, and here we have block size, logical block size. And usually, as I said, on this step, we already know page size and logical block size. So software just takes these numbers from previous elements, from previous structure of elements, and we don't need to adjust here anything. So normally, to apply pair means that we need just drag and drop it here, connect it like this, and that's it. We don't need to do anything else. The question is, how do we know if there are 4 planes? 4 planes we can detect if we will see 4 repeatable patterns within one block, one logical block. Now you have 2, so this is 2 planes. 4 patterns means 4 planes. Now I connect it like this. It's all adjusted already here, so I click to create logical image, and that's it. I can open, and it all looks good. So that's a typical case, typical situation when we have multi-plane page allocation. And it's, as you can see, it's very easy to detect, and it's very clear. Any questions? Okay, so let's open next case. This one. And yeah, it's a little bit more complicated, so let's see it. We have 2 physical images here. First of all, we need to understand if the pair should be used, right? So I open it. Go to scroll it to some data area. Okay, it's here. And you can, as you can see, blocks are quite small here. All right. I think that, yeah, so that's the blocks. And have a look. Let's search for some patterns, like clear patterns. Well, actually, this line is the pattern also, and you can see that all blocks have just one line. one line, one line. In case of multiplane page allocation, I would see second line somewhere here, but I see just one line. The same as here. And to be honest, in many cases, you won't see that much clear patterns, because patterns we can recognize, we can see for some documents or not compressed data. But what is most popular format of data on flash devices? It's pictures, right? And pictures are have quite a big, oh, I forgot this word. Pictures looks quite noisy, and we will not see clear patterns on that pictures. Right, entropy. And but we will see that lines. We still may see the lines for pictures, and these lines may tell us if the multiplane was used or not. And here we can clearly see that multiplane wasn't used. Or, for example, this block. We can see just a noise here, but then some more whitish pattern in the second part. Also different patterns in first part and in second part. So this is how data looks like when we don't have multiplane page allocation. So then what? If we see that there is no multiplane page allocation, we just know that pair shouldn't be used. We should skip this step and proceed with the next one. But since we have here two physical images, we need to unite them somehow, right? To unite them, we will use this element, unite. And the question is how to unite them. Because we can unite it by pages, right? By 2 pages or by 1 page. And we can unite it by dumps. Now let's see how we will unite it in this case. If you remember, I said that it's good way, the way to check how to unite, you should open both elements together and scroll it. And have a look. We can see that second element is actually just empty. So it looks like this device got broken until even first memory chip was full. We don't have data here at all. And the thing is that we shouldn't join them, shouldn't unite them by pages. It's necessary to unite it by dumps. So how I will do this? I connect it like that. And by default, here I have page size. See, area size, it's the size of area which will be used for uniting, which will be taken from this element and then from this element. So now it's page size. And I have a button here which has a D letter, means dump. And if I click, so now area size is 1 dump. That means that unite will take like this amount of bytes, which is actually dump size from here, and then it will switch to this element. So I will unite it by dumps. And if I open it, you'll see that at first I have data from the first element, and then it's just nothing here, right? So this is how, and now I can proceed with block management. Create logical image. There you go. Oops. So this case demonstrates no pair and no multi-page allocation between chips. And as somebody said, this is quite old case, and that's why maybe that multi-plane page allocation wasn't used. Most of cases, majority of devices use multi-plane page allocation. Any questions about this one? Okay, let's move on. Let's see the next one. Okay, same. We have here two dumps, and this one as I said, we may not even open until now. We just work with this one. We did add ECC XOR, and for this element we just added. We just repeat. Of course, we can open it, but I mean, for now we work mostly with the first element usually. And for this one, we just repeat the steps. And that's why we just proceed with the first chain. And now the question is if we should use the pair. Again, I set minimal scale. I zoom it out. I scroll it to some data, to service area. It's here. Now let's see borders of service area. It's from here and to here. Now let's highlight blocks, and I can see that block size is correct. So everything is good. Now I can scroll it to some data areas and search for patterns. And you can see some lines here, and it actually looks like a similar patterns, but let's try to search for something better. For example, this block. You see quite similar pattern in first half and in the second half. So multi-plane page allocation most probably was used. And another thing I'd like to remind you that by default, we always want to use pair element. And we will not use it only if we can find some block with different first and second half. If we even see something like this, and we can't find more recognizable pattern, more clear pattern, this pattern still means that a pair should be used because it's more or less similar, more or less the same. No pair should be used only if you find really different patterns in first and second half. And here you can see that more or less it's the same. And yeah, since we saw two repeatable patterns, for example, here it's quite recognizable. So we have one line in this part, one line in here. Again, I don't know. And since we have just two lines, recognizable ones, we know that this is two planes case. Another repeatable pattern. So pair should be used. Okay, so we know that we have two planes here. We know that block size is correct. Virtual block size is correct. So all we need to do, just drop here pair, and that's it. Once we realize that pair should be used for this chain, of course, we use pair for the second one. We just repeat the steps. So I can use that copy button, or I can drop another pair element. There is no difference. Okay, now we have two pairs. And then how to proceed. I need to unite somehow them, right? How to do this? I open them together, scroll it to some data areas, and check the patterns. And actually, I can clearly see same patterns, repeatable patterns. Same lines here and here. Let's check LBN just in case. How can I do this? I will run hex view, structure view. Do I have LBN here? Yes, I do have. So I'm inside service area, and now here. So that's the LBN. Now let's do the same for the second element. So hex view, structure view, service area. And again, I click here and it will automatically jump. And have a look, FA56, FA56. So LBN is the same. Means that one block was written into both chips, both crystals, FB29, FB29. So this just proves my suspicion that I should unite these two dumps by pairs, or sorry, by pages. Let's do this. Unite, connect it like this, and have a look. The page size here is 8 kilobytes, right? Page size 8 kilobytes. Once I drop unite element to the workspace, it automatically set double page size. Do you remember why should I use double page size? It happens because of this. Yeah, here I had two memory chips. Pages were written like 0, 1, 2, 3. So simultaneously into all planes. After that, we got two dumps. Pages are mixed like this, 0, 1, 2, 3, because this block is from here. This block is from here. This one is this one. This one is this one. So two dumps and pages are really mixed. Then after I used pair will take one page from the first half of the block, next page from the second half of the block. Then it will jump to here, we'll take this page, then this page, this page, this page. And as a result, we'll get two pages go in row, 0, 1, 4, 5, 8, 9, 12, 13, like this. So two pages go sequentially, then we need to switch to another dump. That's why we united by two pages on this step. After we united by two pages, this element will take two pages from here. So we get it in the result dump, and then these ones, 0, 1, 2, 3, 4, and as you see, everything is growing, everything is good here after the unite element. So that's why we united by two pages. And it's quite important to remember and quite important to understand, because there could be, and there are many mistakes here. Because let's see. After you decided that you want to use unite and you want to unite by two pages, you bring this element to the workspace and software automatically set area size of 2 pages. But then it's quite common mistake. People see that they want to unite it by pages. People don't care about that it should be united by 2 pages. They just click to this button, and you see now you have size of one page. That means that unite element will take one page from here, one page from here, and in fact we will get, if we have 0, 1, 2, 3 here. So in the result we'll get like a 0, 2, 1, and so on. So you will really mix pages back, even maybe worse than it was before. So it's quite popular mistake. Pay attention on this area size on unite element. To set it back 2 pages, you can do this manually, of course, or you can connect it like this. And if software knows that, well, actually software knows that pair element is used, it can see this pair element, and software knows the page size, so software understands that a double page should be used. And yeah, so now it's good. Now you just continue with markers table. In this case, it's already done. So I can open the case and see files. Okay. Okay, so this case shows multi-plane page allocation with 2 chips, and multi-plane page allocation was used on planes, on chip level, on planes level. So controller used all possibilities to increase speed. Any questions about this case? All right, and the next one. Okay, so here we have 4 crystals, or maybe 4 chips, I don't know. And as usually, let's check if we need to use the pair element. Okay, this pattern may confuse you a little bit, but in fact this is not SanDisk, it's a Phison, and service area is here. This is pattern of some user data, some pictures probably with some counter. So real service area is here. And how can you see that this is not service area? Because you actually, first of all, you know that this is Phison, and Phison doesn't have service area on this location. And then if you will scroll it, you will find some places where you don't see that pattern on that position. So now I want to check borders of logical block. So here is where block starts, and this is the end, right? And now let's highlight blocks, and it's correct. It's the same. So no need to adjust anything. And now let's try to search for some recognizable pattern. Sometimes you may see such blocks with different pattern in first place, in first half, and in the second half, but it's actually not data blocks. It's some garbage blocks or some system blocks, so it's not user data. We are searching for blocks with real user data, and only that blocks can show us if the multiplane was used. So we skip that ones. And this case is actually looking pretty like most of cases look like when we don't see very clear patterns like we saw before. We see the lines, and as I said, even now you can try to use pair, and most probably you will be right, because pair is default way to multi-plane page allocation, is default way to allocate pages. But just for demonstration, and you can see that first half is more or less similar to second half. But I want to find something, more recognizable for you. I hope I can do this. Oh, maybe not. So maybe here you will see the real common case. I mean, the majority of cases look like. Oh, yeah. So more or less on this block, we can see the repeatable pattern, right? So pair should be used. Pair should be used. We just proved this. Okay, let's do this. Again, we know that block size is correct, page size, of course, is correct. So we just drop pair for all these elements. And now the question is how to unite these four. Okay, let's see. I select all of them, open them together, and let me scroll it now. And what do you see? We can see that 0 and 2 have one pattern, and 1 and 3 has another pattern. Like, for example, now this pattern on 0 and 2. Oops. And now the same pattern on 1 and 3. Okay. So how then I will proceed? That means that data wasn't written into all chips simultaneously, but it was written like this. So I unite 0 and 2, right? And now I unite 1 and 3. So you see, it's like quite complex uniting. We could find very quick. And well, actually now I know already that I should unite this one and this one. How? By dumps, right? But just to make sure, I can again open them and I can see different patterns. Here I see that weird pattern of data area, and here I see some noisy looking thing. So different patterns. To open, the question is how to open together. You just select all of them and then click to dump viewer And then software asks you, how do you want to open them together? If you want to open it side by side, or if you wanted it by tabs, or it's simple view. So you just click side by side, and software will open all of them together. And you will be able to navigate them together. So I will bring one more unite. And if in here it was not necessary to adjust the area size, because software did this automatically. You see the page size 8 kilobytes. Now software sets 2 page size for uniting. And now software kind of stucks because it took page size, because after the unite element, it can't calculate it automatically. So it took page size. And of course, you need to change it. You know that you want to unite them by dumps. So you click on this button and it will automatically set dump size. And then you connect it like this. And that's it. Now you create logical image. And there you go. Okay, pictures are good. And that's it. Any questions? Okay, we are doing good. All right, and now the last one. Open case. And this one. And again, let's see if I should use pair. Don't need this. Let me check block size. Block is from here to here. Each crystal will have the same LBN in service area if multi-plane page allocation was used between these crystals. Okay, highlight blocks, and we can see that block size is good. And right now I can see these two lines, which says to me that multiplane is used. Gain two lines, gain two lines, and as I said, lines are most typical pattern that we can see normally. I mean, for like some photo camera case, because pictures have high entropy and they bitmap of pictures looks noisy even after XOR transformation. So most of blocks have two lines, means that I need to use pair. Okay, let's do this. One pair and the same for another. Now let's see how should we unite all these elements. I open it all together and have a look. What do we have here? I would say that we have same patterns within all dumps. There is a version to unite it 0 plus 2 and 1 plus 3, but actually not. We can see that patterns, well, maybe yes, this one and this one look more similar, but in fact, any place or most of places will show same looking patterns. The thing is that patterns have not to be exactly the same, because we understand that they appear because of this. Yeah, because of this data writing. So data has not to be, pattern has not to be exactly the same in this part and in this part. It should be similar. The main word here is similar patterns, but not same patterns. Okay, so we can see that most of places have similar patterns. This says that we need to unite all 4 dumps by pages, right? By 2 pages. And now the question is how exactly? So I bring unite element, and here in parameters I can set number of inputs. So I can set 4 inputs for unite, and you can try to unite it like this. Yes, page size, it was 4 kilobytes, now it's 8 kilobytes, so it's correct. But it's good to make sure that this order is correct, because it can be different. For example, data could be written first in this dump, then in this dump, for example, or it could be somehow mixed. You don't, in case if you have several chips, you may not be sure which one is the first, which one is the next one. So in such cases, well, you can just try to use a straight order, and if it will not work, you can try to figure out this. And for this, we will use kind of the same approach like we use for RAID recoveries. If you are familiar with the RAID recoveries, you know that the order question, I mean disk order, is one of the main when you do RAID recovery, and you need to detect which drive was the first, which drive was the next, and so on. And usually you do this based on some file system structures, because file system structures, usually they have counters, some increasing byte. And if you will check this byte, value of this byte on the same position on all elements, on all drives, you will see which drive was the first, which drive was the next, and so on. Now let's try to use the same approach. And to do this, first of all, we need to find that file system structures. To do this, we may use this tool, file system metadata. When we run it, we can select what file system we want to search for, and usually it's FAT32. I mean, for majority of devices, we use FAT32, so you can start from this one. If you know that, if you suspect that there is another file system, you can select another file system. But normally, we start from FAT32. And then you click to the start and just wait. The question is, there is a question, what's going to happen if we unite 1 plus 3 and 0 plus 2, and then what? And then if you will unite it, like you will create 2 unite elements, and if you united this one and this one, then this one and this one by pages, and then you will bring one more unite element and unite it again by pages. So the result may be quite the same, but you will do this in 2 steps. And in here you will unite it by 2 pages, then on the next element you will unite it by 4 pages. And but you can do this just within 1 step, so it's just not necessary to use this approach. You will be able to assemble it, but you will just not see data. I mean, if you will set area sizes correct on first unite elements and on second unite elements, it will work, but you will have to set correct area size elements. Because if you will unite on first unite by pages and then you will unite it by dumps, it will not work. It will not show you any data. Like this, for example. Let me bring. So you have 2 unite elements, you unite it like this, right? And then you unite it 1 more time. So then you can unite it like this, and if you will set correct size of uniting here, it may work. But it's better to, I mean, it's more clear, I think, and easier to use just 1 element, so it will take page from here, and so on. Okay, so the system, the VNR found some bytes, some areas with the file system elements. And for now, we don't see which ones, so we can just open it like this. And let's enable hex view, and immediately we found some place where we have these counters, the FAT tables. And now if we open the same place on all dumps, we can compare the counters and we can understand which dump is going to be first, which dump is going to be next, and so on. So how will I do this? I can actually do it like this. I select all of them, click to dump viewer, open all of them, and yes, I close bitmap view and run hex view. Now it's more clear for me to use because I can see the numbers. Okay, and let's select this byte. and we can see these numbers, right? And do you see which result was the first one, which pair is the next one, and so on? Now we just compare these hex values, and the minimal one will be the first one. So next one will be the next, and so on. And which one is the minimal? Here we have 8162, 8172, 816A, 817A. So the minimal one, I would say it's this one, right? 8162. The next one, we have 726A, 77A. So this one is smaller than this one and this one, right? So I would say that after pair 0, we have pair 2, right? So the order would be 0, 2, and then after 6A, we have two options, 72 or 7A. 72 is smaller, then so it's going to be 72 and then 7A. So the result order will be 0, 2, 1, 3, like this. Okay, let's connect it like that. Zero, 2, 1, 3. And I united by 2 pages. Do you remember? Still by 2 pages. And page size 4 kilobytes. After pair, it's going to be 8 kilobytes. And software automatically set it like this, 8 kilobytes here. Okay, now what should I do next? I just connect it like this. Create logical image. And it's good. And that's it. This is how we unite elements in such situation. You see, it's a little bit more tricky when it comes to detect order, but still not that hard, not that complicated. So thank you for today to all of you, and see you tomorrow then.